In this video, we'll look at some approaches for implementing integration techniques in MATLAB. After studying this video, you should be able to use MATLAB to compute integrals of discrete data, like what you might have from running an experiment. Also, you should be able to use MATLAB to compute integrals of functions, like functions that are impossible to integrate, like the e to the x squared integrand that we talked about previously. The first MATLAB function for integration that we'll talk about is the trapz function. And this function implements the composite trapezoid rule to calculate the integral of data that's input in a vector. The output is going to be a scalar that's the integral of that entire vector. If you give trapz a single input, the function returns the integral of the data in y, assuming that it has equally spaced data with h equal to 1. So that's like an integral from 0 to the length of y dx would be a way to think about that integral. If you call trapz with two inputs, x and y, it will integrate the data in y with respect to the data in x, going from x1 to xn in whatever increment the data x has. And that data does not need to be equally spaced. Another MATLAB function that you can use for integration is the trapz function. And this function implements the composite trapezoid rule to calculate the cumulative integral of the input data. And the difference here now is the output is a vector. And here's how you can think of trapz. So if you give it a single input y, it will again assume equally spaced data with h equal to 1. And each element of the output vector I will be equal to the integral starting from 0 to whatever position, and again we're using increments of h equals 1 in y dx. A way to think that might be a little bit more intuitive is to think about the case where we give trapz two inputs, x and y. So now that each element of I is going to be equal to the integral from the first element of x up to the corresponding element of x to that element in index. So what that output vector is going to look like is the first element would be the integral from x1 to x1 of y dx, which of course is going to be equal to 0. The next one would be from x1 to x2 of y dx. The next one would be from the limits of x1 to x3 of y dx, and so on all the way to the final one, which would be still a lower limit of x1 up to x end. And again, for trapz, the data does not need to be equally spaced. Let's talk a little bit more about this difference between trapz and trapz. Might be easier to understand in the context of an example. So suppose you're integrating velocity to calculate position of an object, and the velocity is given by simple equation v equals t squared, and we want to calculate the position of the object for the first 10 seconds of the motion. So first of all, both of these functions are for integrating data. So the first thing we need to do is sample our function to generate data. And I've just sampled the function on intervals of 2 seconds to generate t and v data here. Now if we use the trapz function, we would be calculating the total displacement after 10 seconds. So that's the equivalent of taking the integral from 0 to 10, so from the lower limit to the upper limit of t squared dt. So that trapz of t and v, again giving it that x vector, we would find the total displacement comes to 340, which is equal to 10 cubed over 3, roughly. Remember, this is a numerical approximation. 10 cubed over 3, which would be the exact result, is actually 333. Cume trap z would be analogous to calculating the integral that would give us a position as a function of time, where that integral is from 0 to t of t squared dt. And so that output again is going to be a vector, where the first element is the integral from 0 to 0. The second one would be the integral from 0 to 2. The third would be the integral from 0 to 4, 0 to 6, 0 to 8, and finally 0 to 10. And you'll note that that last result, 340, is the same as the result 340 that we had for just trap z. So let's look at another more detailed example of calculating the integral of some data using MATLAB. So here's some velocity data again as a function of time. It's not equally spaced, and we're told that this data does include some measurement errors. We're going to determine the position of the object using three methods. First, we'll use the trapezoid rule directly on the data. Next, we will fit the data with a cubic polynomial, so we'll do a curve fit and integrate that result analytically. And third, we'll fit a cubic spline through the data to generate interpolated data on 0.1 second intervals, and then we'll integrate that again with the trapezoid rule. So here's an M file to do this calculation. First, to integrate with the trapezoid rule directly, we can just use cume trap z. Then we'll do a curve fit, so here's polyfit to do a curve fit of that cubic polynomial. And then these next two commands calculate that analytical derivative of the polynomial. Sorry, analytical meaning exact integral of that cubic polynomial. And what I'd like you to do actually is work through these two commands by hand and look at what they're doing and make sure you understand how these two commands are working to calculate that integral. The spline fit is the last method here. So first we'll generate interpolated data. So there's our interpolation. And then just using cume trap z to integrate that interpolation. So let's look at all these results graphically. So here's our data along with the cubic curve fit in green, and the spline, which goes through all of the data points, in red dashes. And in the lower subplot here, we have the integrated data directly, so the stars are integrating the data directly with cume trap z. The green line here is the integral of the cubic curve fit, and the red dashed line is the integral of the spline interpolated data. And one important thing to note here is that all three approaches yield near identical results. So we're using a fairly coarse data spacing, and there's obviously, when we look at the data, if we assume it's not really oscillating, the data has quite a spread in terms of errors for that curve fit. But contrary to differentiation, the integral tends to smooth out the errors, and all of these approaches yield very similar results. So next, let's talk about integrating functions. And MATLAB's built-in functions for integrating functions all use adaptive quadrature. And I briefly mentioned this before, and I'll explain it more in this context. So there's two built-in functions for implementing adaptive quadrature. One is a function called integral, and that implements adaptive quadrature using a Gauss-Kronrod algorithm. And this is the recommended function for general use for integrating functions on MATLAB. The way Gauss-Kronrad works, it's similar to the Gauss-Legendre formulas that I discussed in the Gauss quadrature video, but it has a key difference in how the constants are determined. So it's still a case where we're going to approximate that integral with a linear combination of function evaluations, where we have to determine the weighting coefficients and the x values where we take those function evaluations. But the difference for Gauss-Kronrad is it's set up such that it starts with a lower order Gauss quadrature, say a 3-point approximation, and then compares that to a 7-point approximation. So always adding n plus 1 points. And that 7-point approximation includes the same 3 function evaluations that the 3-point approximation uses. And that's the key element of the Kronrad approach to Gauss quadrature, is that to get a 7-point approximation, we only need 4 additional function evaluations. And the way that this will work is it's an adaptive quadrature algorithm, so that it'll calculate the integral with 3 points, then it'll calculate the integral with 7 points, it'll compare the two results and calculate that approximate error, and if the approximate error is greater than the tolerance, it'll go ahead and calculate it again with 15 points. We'll talk a little bit more about that in a second. Another MATLAB function for numerical integration is the quad function, and I mentioned that here because that uses adaptive Simpson quadrature. So again, that's using Simpson 1/3 rule. And the way that works is it adjusts the interval size based on successive calculations using Simpson's rule, and then checks the approximate error against an absolute error tolerance. So you can imagine doing a composite Simpson's rule calculation for a region of the function using more segments and comparing that to the one using less segments, and calculating that error between the two, and if that error is greater than the tolerance, then the function will iterate and calculate it with even more segments and calculate the error again, and continually add segments to the integration until it brings the final error below the tolerance input. Let's talk more about the integral function, since that is our general use integration function. The syntax for using the integral function is we'll give it a function, and again that is usually an anonymous function. That's how we define that. A and B are the limits of integration. And then the options for the integral function are set very similar to how, if you recall, we did the optim set command for functions like f0 and fmin search, but in this case they're actually included right in the function. And the most common parameters to set are the relative tolerance and the absolute tolerance. The relative tolerance has a default of 1 times 10 to the minus 6. The absolute tolerance has a default of 1 times 10 to the minus 10. And again, the way integral works is it increases the number of points in the calculation, and doing that with that Gauss-Kronrad approach that minimizes the number of additional function evaluations. And again, we're doing that for computational efficiency. We increase the number of points in the calculation until that integral with more points minus the integral with less points, until that absolute value is less than or equal to the maximum of either the absolute tolerance setting or the relative tolerance setting times, again, that's our more accurate estimate. And so basically what we're doing is we're continually increasing the number of terms, the number of points in that linear combination of function evaluations until the end integral result is changing by less than the tolerance setting. So here's an example using integral. The velocity of an object here is given by this function. V is equal to 10e to the negative t squared times cosine of 2t. The object starts from rest at s equals 0. The object starts at s equals 0 with this velocity, and we want to integrate the velocity to find the position for the first 3 seconds of motion. So we'll define that velocity with an anonymous function and set up a vector of t values. And now to find s of t, so we're trying to find a function s of t, what we need to do is do a for loop. The first value, s1, is going to be 0 since it starts from s equals 0, and we've set that by how we pre-allocated our vector s with the zeros command. And then we're going to go from 2 to length t, continually calculating this integral. So each time we do this integral, we'll go from 0 to t1. Then the next time through the loop, we'll go from 0 to t2. Next time through the loop, 0 to t3. Again, where t1 is our first non-zero value of time, t2 is our second non-zero value of time, etc. So we need to do that in a for loop, because otherwise integral is just going to output a scalar that is the total integral of the entire range. So I've just shown a plot over here to show what we get using the plot yy function, which I don't think I've introduced before. That's nice because it lets you have two y-axes. I've got one for velocity and one for position here. And you can see how we're able to plot the velocity starting at 10 and oscillating down to a final velocity of 0, and the position starts by increasing rapidly and then slowly settles in to a position of about 3.5. So I'd encourage you to download this code, make sure you understand how it's working, and this concludes our video on MATLAB's integration functions.